Hi, welcome to Paper 3. My name is Bill, and let's jump right into it. I have chosen the paper called Improving Data Analytics Performance via Autonomic Control of Concurrency and Resource Units. The keyword here is the autonomic control. This paper is by authors Gil J. Lee and José A. B. Fortes. The venue and year is ACM Transactions on Autonomous and Adaptive Systems 2019. I think about March as well. Right, so the problem addressed by this paper is in big data processing and the use of data analytic frameworks to process data. And the key takeaway is that actually the tuning of configuration parameters as part of data processing is actually manually set. And this is often by expert software developers or data analysts. And so the key idea is, going back to the name of the paper, autonomic control, is to ensure that this tuning process can be actually automated rather than done manually. So the solution that this paper has presented to this problem of having to manually tune the configuration parameters of data analytic frameworks, specifically the example that they refer to as Apache Hadoop for big data processing, is that they've introduced this framework which is called this architecture that's called the hierarchical self-tuning architecture. Now the key word to think about is the word hierarchical, as it's different from the existing techniques that are used to actually automate or deploy models that to configure the tuning of these data analytic frameworks. And yeah. So some related work in this area include model-based tuning techniques. It's important to note that training is time-consuming. So training models, you have to basically gather all the data, and then you have to process all that data, and then you have to feed it into your model. And then once you've fed your model, you have to generate the parameters, the configuration parameters that you need, and input that into your data analytic frameworks. And then also repeating this process is also much more time consuming, especially when and other potential issues that can occur is when the environment that the model or the data analytic framework is working in is changing. So in terms of data utilization, like how is the system that's processing the data, how is it adequately utilizing the resources available on that in that system or on that server itself, and basically having all these parameters and putting it passing into the model and basically using that data is actually a time-consuming process. So talking about the solution architecture of this hierarchical self-tuning approach or architecture that they've introduced is actually composed of 4 components. So that's a global controller, a global monitor, a local controller, and a local monitor. And and I'd like to use this moment to reference the assignments that we've done of the Python simulations, and this basically some of the self-adaptive systems theories that we've looked at. We've got like controllers which kind of they take in the information that they receive from the monitors, and then they manipulate that information and basically introduce changes into the system based on the information that has been retrieved via the monitor. And so effectively the same concepts can be carried through into this paper and how they've basically built up their architecture here, and which we'll see in the next slide. So I'll go straight to it. Here is an example carrying on forward from the architecture we described in the last slide. We described the components of a global controller, a global monitor, a local controller and a local monitor. Here, if we take a look at figure 1, on the master node, you'll see a global job controller, a global resource monitor, and these are the kind of the equivalents in this setup. And in the slave nodes, you see the local task controller and the local resource monitor. So the local resource monitor basically monitors the resource like the CPU usage, the number of tasks that are done, like all the miscellaneous necessary information about the data analytics framework on the slave nodes, and then passes that to the controller, and the controller makes the decisions and interacts with the manager, and at that, on the slave node level, any changes that need to be applied at that level are executed. At the same time, the monitor also passes all that, the local resource monitor also passes that information to the global resource monitor, so that on the higher level, that the master node can kind of globally see across that all the slave nodes how the CPU and resource utilization is, and subsequently make changes at that level as well. And so this master and slave node kind of relationship here is really what describes and defines the hierarchical self-tuning architecture, the hierarchical word in that framework or proposal. In figure 2, you have the resource usage, an example of basically the level of utilization when resources are provisioned and under-allocated or over-allocated, and the number of jobs that are actually being in each situation. The evaluation process of evaluating whether this hierarchical self-tuning architecture is really applicable or equatable to just the optimal tuning, manual tuning of an expert data analyst is pretty visible here. They've conducted 4 different tests of different jobs. Here they have, in their original experimentation, they talked about using a 10 slave node Hadoop cluster processing 200 swim jobs. In this diagram, it seems like they've provided comparisons of different jobs and of different quantities, of 500 actually, I should say, so same quantities, and the average CPU utilization when processing those jobs by this 10 slave node Hadoop cluster. So what's immediately visible is that both the static optimal and the hierarchical self-tuning architecture both performed significantly better than the default configuration for the default self-tuning parameter configurations in pretty much every single case. It seems that the hierarchical self-tuning architecture is not necessarily optimal in all cases, but is very, very comparable, and the key difference is that you do not need to have someone who's an expert manually configure the properties or the configuration properties of the data analytics framework for it to kind of be on par. So in terms of the amount of time saved and resources better utilized, this kind of framework can automate that process, so you don't have to have an expert coming in and manually tuning it between jobs every single time. And I think that based on this simulation, there's very real evidence to support that this kind of hierarchical architecture is actually could be viable. So the researchers have concluded that the HSA that they've described is able to improve performance in data analytic frameworks, and it does so by maximizing CPU utilization. And the key concern that they actually had, the key takeaway they had from this was that they actually only consulted 2 resource usages that they monitored on the local slave nodes, and that was CPU utilization and disk I/O. So although it's pretty good at the moment, it can definitely be improved by considering other resource factors in the future works, which I can't really think of off the top of my head. However, yeah, there's definitely ways to go to expanding and improving on this, and it draws eerie similarities between what we have just worked on in assignment 2 in our Python simulation. Um, so I guess in a way I'm quite more fond of this paper, and I'm biased for that reason, because I just spent ages coding up a simulation that kind of works off CPU usage as well. Oh yeah, thanks. Nothing else to add.